Thank you. Can people hear? Well, I want first to express how honored I feel to be part of this wonderful event, and thank the organizers deeply for including me. I think we're getting some feedback, I'm not sure. And of course, I want to extend special thanks to Abner for many things. And I won't even attempt to enumerate them all, but just a few highlights. First, for writing the Bell Bible. It was already referred to in an earlier talk, the paper with Clauser of, I think it was 1978, was it, in Progress in Physics, surveying the results of theoretical and experimental results up to date, which made it possible for me to start thinking seriously about the subject. Further, and more personally, for his very helpful and probing discussions of locality concepts, which extended over some years. We met at Philosophy of Science Association meetings, I believe, and I think also we were on a National Science Foundation panel together back in the early 80s, and had some extended discussions at that point, and then on the telephone and through correspondence. This led to work that I did on generalized Bell inequalities. Without Abner's encouragement and critical feedback, I don't think it would have happened. Then I would want to thank him for the whole idea and promulgation of the idea of experimental metaphysics. This was a very inspiring idea for me, and I think to many people working in the philosophy of physics, and continues to inspire us. And then for helping to revive the whole area and idea of natural philosophy after too long a hiatus, I think, especially in the early 20th century, due to the increasing specialization of physics and maybe some other cultural tendencies that would be interesting to try to analyze. But there developed, I think, a gulf between physics and philosophy that was unfortunate. And I regard Abner Shimony as a force in the late 20th century to overcome this separation and help bring about a reemergence of a fruitful interchange between the two great fields. Well, today I actually won't be pursuing something that could properly be called experimental metaphysics, but rather engaging in one other related complementary enterprise which philosophers can do, or should be able to do, conceptual analysis of a sort. I'm focusing on concepts of probability in quantum mechanics. My title is a bit inaccurate. It would be better to say some interpretations of probability in quantum mechanics, but philosophers do too much hedging as it is, and so I didn't want to do that for a title. But if you don't see your favorite interpretation of quantum mechanics mentioned in the talk or displayed on the overheads. Despair not. I hope to finish in time so that in the discussion there'll be an opportunity to take up others that I don't consider here. So now I take for granted that the mathematical apparatus for treating probabilities in quantum mechanics is quite well understood due to the work of von Neumann, Lüders, Mackey, and culminating in the famous theorem of Gleason characterizing measures on the closed linear subspaces of Hilbert space of sufficient dimension 3 or greater, as given by the quantum algorithm via trace class statistical operators. I want to just remind you briefly what that apparatus looks like. And so recall that states can be represented as density matrices, double labeled W, positive self-adjoint operators such that for any orthonormal basis of normalized vectors psi k, you get the sum of those inner products summing to 1. And then we define the trace of WB for B, a bounded linear operator, and a given orthonormal basis. As indicated, it's that sum over the single index J, that's the trace of WB, and the operators commute under trace. And the traces are independent of the choice of orthonormal basis. That's very important. And then there's an important theorem of von Neumann that if you have a finite expectation value, expectation B, defined for all bounded operators B, then there's a unique density matrix W, which satisfies the trace equation there at the bottom. And it's assumed that the expectation satisfies the conditions that if B is a self-adjoint and positive, then the expectation of B is real and non-negative. That you have an expectation of a scalar multiple of the operator behaving in the appropriate way algebraically. And now here, the sum principle, this is a sum of operators, and expectation of the sum is equal to the sum of the expectations, and that the expectation of the unit operator is 1. And then for mutually orthogonal projectors, E sub k, you have linearity as indicated. Notice that the condition for finite sums doesn't make any restriction to compatibility of to compatible operators or observables. This is a weakness in the von Neumann definition here. It led to von Neumann's no-go theorem, the hidden variables theorem, the no hidden variables theorem that was accepted for quite a while as ruling out hidden variables. But it was precisely this condition here, this sum principle, which does hold in quantum mechanics. It makes sense because we're talking about algebraic vector sums, not sums of values. So this does make sense in quantum mechanics, and it's correct. But it should not be imposed on a hidden variables reconstruction of quantum mechanics. But I just mentioned that to remind you of a little bit of the history of the debate over hidden variables. But in any case, this is still a useful definition. A quantum state can be taken as represented by a unique density matrix W. And then if we look at B, restrict B to projection operators E, then this finite expectation of E is a normalized, generalized probability. And So then the last condition here generalizes the notion of disjoint additivity. And so we have mutually orthogonal projectors there, so compatibility. And now recall that projection operators are in 1-1 correspondence with the closed subspaces of Hilbert space, representing the Hilbert space representing the system, and subspaces in turn correspond to quantum propositions of the form observable A has a value lying in Borel set B. That's a way to think about quantum propositions and connect that up with the formalism. So in effect, a density matrix assigns a probability P of S to each subspace S via, or each proposition S, via the trace formula as indicated. And in the case of a pure state, that corresponds to more familiar notation, projection operator phi. Where's my next slide? Here we are. And if the state is mixed, we take a convex linear combination of such states. And so it's clear that the quantum pure and mixed states do furnish generalized probability measures on the relevant structure, the closed subspaces of Hilbert space. The question then was, are there any others? This was a question formulated carefully by Mackey. And the answer was proved to be no, and that's the famous theorem of Gleason's, which I've put up here. Let a Hilbert space be of dimension greater than 2, and let brackets E, map projectors E to non-negative real numbers, obeying that the unit is 1 and additivity for any set of mutually orthogonal projectors. So here there's no requirement that non-commuting, sums of non-commuting operators be preserved. Then there's a unique density matrix W, such that the expectation of E, which is a probability, is given by the trace of WE for every projector E. And so that generally settles the question of how to understand probability formally in quantum mechanics. However, the machinery is open to multiple interpretations bearing on physics and experiment. And it's our purpose here to survey these briefly with the aim of clarifying the meaning and place of so-called objective interpretations of quantum probability. It's unfortunate we maintain that interpretations of quantum probability have been labeled simply objective and subjective, for this encourages conflation of issues that must be kept distinct if serious confusions are to be avoided. These issues pertain to two dimensions integral to the very concept of probability. The first issue concerns the values of probability functions, the real numbers assigned lying in the interval 0, 1. The question here is what, according to a given interpretation, quantum probabilities measure. For example, do they measure actual relative frequencies of experimental outcomes in ensembles, or limiting values of such frequencies taken over idealized infinite sequences of such outcomes? Or do they measure strengths of physical dispositions of systems to behave in various ways if they undergo or were to undergo various interactions with other systems? Might call these propensities in one sense of that term. Or do they measure degrees of belief that a rational betting agent given certain specified information, would have in this or that prediction about the system. So I call this dimension 1 of objective-subjective. And one could reasonably classify these possible answers as objective or subjective. Presumably, relative frequencies in ensembles are an objective matter. They are strengths of physical dispositions of individual quantum systems, whereas degrees of belief or certainty of agents are not unreasonably termed subjective. Here, actually, I think the word anthropocentric would be a better choice than subjective, but it has too many syllables. So, now perhaps this is the primary meaning of the objective-subjective dichotomy that discussants of the subject have had in mind. But there's a second dimension which, from a foundational point of view, is equally important and which intrudes itself upon all the examples mentioned so far. And that concerns not the values of probability functions, but rather their domain of definition, the events on which they are defined, the bearers of probability, as it were, or what the probabilities are probabilities of. Now, here, of course, in the purely mathematical sense, we know what the domain of definition is. It's the lattice of subspaces of the Hilbert space. But now I'm asking, what does that mean on an interpretation? What does that correspond to? So, we say, in connection with the options already mentioned, we may ask relative frequencies of what, described how, or strength of dispositions to do what, described how, or degree of belief in what, described how. In classical mechanics, these issues are not problematic. Probabilities are assigned to measurable regions of phase space, and these are understood as collections of physical states in which certain physical magnitudes are possessed by the systems in question. So there's objective possession of properties. Probabilities are probabilities of possession of properties. Indeed, states can be considered essentially as lists of properties. Certain key ones, of course, phase quantities. That, of course, is notoriously not the case in quantum mechanics, except under certain non-standard interpretations. It's decidedly not the case in textbook quantum mechanics. Indeed, in order to avoid contradictions that naturally arise in the peculiarly quantum mechanical context of incompatible observables, one has resort to talk of properties not simply possessed by quantum systems, but found to be possessed if suitably measured, in which the essential move, which is the essential move in the doctrine of complementarity. Pure quantum states can be taken as extremal probability measures on closed subspaces of Hilbert space, which specify how systems would behave, what properties they would exhibit, if observed in this or that specified way. Even this is controversial, resting on inference from the observed apparatus system in a measurement to properties of the quantum system itself. And interpretations appealing to complementarity of the Copenhagen variety, broadly speaking, range from more objective and licensing such inferences to completely operational and banning them entirely. So now the simple classical language of property possession, a purely objective matter, has been replaced with a complicated reference to a variety of possible outcomes of interactions. And these themselves are described with language, frequently employing and bringing in big, bad words like measurement, observation, and so forth, which are not yet explained physically and which refer obliquely to cognitive agents. That is, the events assigned probabilities have subjective elements in their common descriptions. This is dimension 2, and it also can be divided broadly into objective and subjective sides, where objective applies to probability bearers described in physical language without reference to those, without use of those problematic terms like measurement, observation, appearance, and so forth. And subjective can be used to apply to bearers whose description does not make any such reference. So, and this leads to a 2-by-2 matrix of possibilities. Is that visible? Where we just consider those. And I should say here, I recognize that this is somewhat crude, that there are many subtleties in the interpretations, even the ones that are considered here, that would need to be considered more carefully if one were to do a more serious classification. But I think this is a helpful first approximation, that these distinctions are important, and that leads naturally to these four cells. And so, and I should also say that, well, there are a number of interpretations that will be familiar to many of you that don't appear here, and we can talk further about those. And also, final caveat that sometimes an interpretation maybe in some respect sits in another box as well. So you can have a kind of hybrid classification. It's a kind of, it allows for hybrids. So with that understood, though, let me just say something about the various occupants of these cells by way of illustration. So under objective, here are features of one class of interpretations that fit quite clearly under this heading called modal interpretations, going back to work of Simon Cochin, a mathematician, and added to considerably by the work of Richard Healy, Dennis Deeks, Pieter Fermat, and Rob Clifton, and others. And the idea in these interpretations is to appeal to certain features of the quantum formalism. In the case of Cochin, Fermat, Deeks, to the uniqueness of bipolar decomposition of a wave function of a joint system, typically thought of as a system including an object system to be measured and a measuring apparatus, but the whole thing is general and doesn't depend on the use of those, it doesn't depend on those descriptions. And so it's a theorem that a joint state can always be expressed as a sum of product states over a single index. The general expression would have two indices. You have psi ij, phi I, psi j. But here you can, in the bipolar decomposition, you just have one index. So it's what you would like to have in a good measurement setup at the final, state. If it's a non-disturbing measurement and so on, you would like to have a correlation, a perfect correlation between the eigenstates of the observable the system, quantum system being observed, and those of the corresponding pointer values. In cases where you have this bipolar decomposition, or that is, you look at the bipolar decomposition, and then you say that actually this licenses going beyond the quantum formalism as we ordinarily understand it, and attributing the associated magnitudes and values to the systems themselves. And so pointers do point after a good measurement. However, the quantum state, this is not an application of the projection postulate. The quantum state continues to evolve, of the joint system continues to evolve. So it's a supplementation. It is a hidden variables interpretation, but it's a partial hidden variables interpretation, and it does not run afoul of the no-go results of Gleason, Cochin-Specker, and famously Bell, precisely because of its partiality. I said their partiality, we're talking about it. There are a lot of variants of this modal interpretation idea. And crucially, they all give up the eigenvalue-eigenstate link, which is a key feature of standard textbook quantum mechanics. You say that an eigenvalue is not possessed by a system, eigenvalue of an operator or observable is not possessed by a system if it's not in an eigenstate of that eigenvalue. Right? But here, that's given up, and more values are assigned. But it's done carefully so you don't run afoul of the no-go results. Probabilities are of possession of properties. But the latter are quantum mechanical. So that's the objective in sense two. Good measurements revealed these properties. But measurement is not primitive. Rules are framed in terms of quantum interactions or the mathematical form of states. And so bad words are avoided. Now, very important, ultimate physical randomness is recognized. Pure states give measures of strength of dispositions to actualize various values and interactions. So now this isn't true for all things that are called modal interpretations. But I think that reflects somewhat badly on the classification of modal interpretations that ignores this distinction. The Cochin, Dieks, Healy versions, Fermat versions, do respect this feature that is also recognized in many other interpretations of ultimate randomness in nature, and I take that to be extremely important. It's not reflected, it's not respected in Bohm's hidden variables theory, as we'll see in a moment. Okay, so there's this talk of dispositions as objective. Main challenges to this are the problem of Lorentz invariance and extensions of the interpretations to quantum field theories. And these are outstanding problems, and there's a great deal of work that's been done on this, and we won't be able to go into it here. But I should also add now, and at the very bottom, I have some scroll. Another occupant of this objective one, objective two, or I suggest it's an occupant, is the GRWP theories of spontaneous collapse, which is an objective process. And as I understand it, and we'll hear, I believe that we'll be hearing much more about this afternoon, and perhaps Philip can answer questions here about where that interpretation should sit in this table, but I do believe it is up on the objective corner, which is very interesting. So that the probabilities are probabilities that nature will just collapse in one way rather than another with greater frequency or greater with a stronger disposition, which is very much in the objective sense. Okay. Now moving on to the objective one, subjective two. Yes, this is nicely illustrated, I think, by certain texts, certain textbooks in quantum mechanics. Famous one by David Bohm from 1951. I believe, fits this category very nicely. The eigenvalue, eigenstate link is respected. Probabilities are of measurement outcomes classically described. Recording apparatuses are taken as given. So these concepts are used freely by Bohm. You know, in this sense, it's Bohrian. That's why we have subjective too. The big bad words are in there on the ground floor. There's no attempt to explain them away. However, probabilities do measure strengths of complex physical tendencies. Tendency is the word that Bohm preferred. He didn't use the word propensity. Or dispositions to reveal values of measured observables. Ultimate physical randomness in the realization process is allowed for and recognized. So quantum pure states are thought of as complete in the sense of physically complete. There are no further values to be had there. There are just these spontaneous but probabilistically law-like governed outcomes. Yes?
You remember subjective two. That two means what are the probabilities of?
Yeah. Of measurement outcomes, of.
Say probability falls on measurement outcomes are subjective rather than objective.
The probabilities are described, it's the probabilities of what, and they're described using these subjectively loaded terms like measurement or apparatus or what we observe. That's the key thing here in the second dimension, is the use of those words that bring in the observer. So there's this kind of observer dependence of how you describe what the probabilities are assigned to. It has to do with the descriptions that we give of those things. Well, measurement, see the notion, I'm taking that as a bad word too, if you just say measurement as primitive. If you say interaction, obeying Hamiltonian of this mathematical form, that's okay. Modal interpretations do that. But Bohm goes well beyond that, and he needs to. So he has the cut between the quantum world and the world with our background conceptions that we bring to the quantum world. Yeah. Well, I wouldn't. No, I don't want to put it that way because I want to allow for something objective to supplement the quantum formalism, such as the GRW. So I would put it in terms of the use of these bad words, and I just try to list those. And we could, you know, we can quibble about whether. Yes, right. Anthropocentrism would be a better term there. I agree. Now, okay, so then I just list a few drawbacks. There's the need for a cut between quantum and classical domains. How do we make sense of the wave function of the whole universe? And then there's the business of how Bohm, at this stage, dealt with the measurement problem. It was a very ingenious idea, and it's a precursor, I think, of what's now kind of favored by a lot of people, the decoherence solutions. So randomized phase factors are said to enter when a quantum system comes into interaction with a complex many degrees of freedom system. These phase factors, when you average over them, the interference terms virtually vanish. But it's a FAPP solution in the sense of Bell, F-A-P-P, for all practical purposes. It's not a genuine solution. Okay, so now I'm running out of time a bit. How much? Okay, good. Now moving to the objective 2, subjective 1 side. So here we avoid the use of any of these bad words, but we have we have subjectivity in that the probabilities measure relative frequencies reflecting our ignorance of actual underlying positions and velocities. So this is Bohm's hidden variables interpretation of the, actually, I think it's 1952. And I've given the URL there where you can get some very good detailed information about the formalism. It's really pretty compactly presented there. The eigenvalue-eigenstate link is not respected. Definite positions are assigned to systems at all times. Probabilities are of possessed properties, possessed position properties. All quantum observables are reduced to position. So that's a feature of the Bohm hidden variable theory, that everything has to be ultimately explained in terms of positions of something. Probabilities measure relative frequencies, but relative to ensembles reflecting our ignorance, as said. And so there's a subjectivity comes in here, or observer dependence comes in that, you know, if we knew all there is to know out there in the physical world, we wouldn't need probabilities. The theory is completely deterministic in its evolution, right, as long as you focus on position observables. And so probability is called subjective here for a somewhat different reason, but it's because the whole need for it arises because of our own ignorance. So it's an epistemic necessity. And there are results. It's built into the Bohm theorem that any experiment you do in physics is going to respect the Heisenberg uncertainty relation. So it's going to look as though there's all kinds of randomness going on. But that's really an illusion, and this is the beauty, or maybe not, of the Bohm theory. Ultimate randomness is not recognized, as just said. And so here are some key features at the bottom. No quantum classical cut, no measurement problem. That the main challenge is there's a high degree of non-locality. And how does one extend it to relativistic quantum fields? Again, an ongoing research project. And finally, the last quadrant, subjective. And here, this would apply to particularly instrumentalist versions of the Copenhagen. Very different from the Bohm textbook version of Copenhagen, which is just got 1 foot in the objective side and 1 foot in the subjective side, as I've classified these things. But here, the eigenvalue-eigenstate link is respected if values are assigned to microsystems at all. And in an extreme version, we needn't assign any values ever to a microsystem. All we need to do is talk about the recording instrument's properties, right? Probabilities measure relative frequencies in experimentally selected ensembles or degrees of belief of rational betting agents. And particularly in the latter case, there's a reason for calling this subjective in the sense of subjective 1, degrees of, the numbers are measuring degrees of belief. And if the degrees of belief are degrees of belief about outcomes of measurement, well, then you have subjective 2 as well. And so, or pointer readings or appearances thereof, so that's already covered. So now, this appears to avoid theoretical problems, the realization of definiteness, the measurement problem, and so forth. But it provides no physical explanation of observed frequencies. And so the worry here is that such approaches seem to renounce the enterprise of physics. Now, finally, I want to consider, does the subjective quadrant really offer refuge from the measurement problem? I was inspired to put this slide together because of a talk that I heard recently from Jeffrey Boob, in which he seemed to be suggesting precisely this, that if you took this, if you worked within this information theoretic reconstruction of quantum mechanics and interpreted probabilities as simply as a Bayesian would in terms of degrees of belief, then somehow the measurement problem would go away. And so here's a reminder based, I believe, on a wonderful paper that Abner himself wrote for Scientific American way back when on foundational problems in quantum mechanics. That problem arises from three, and only three assumptions. The first I call universal applicability of quantum mechanics. And now universal maybe is too strong, and there are different versions of different ways to generate the measurement problem. And you can certainly do it with much less than full universality if you think that it's contrary to reason to say that computer printouts don't actually reveal, ones or zeros, then you don't need, all you need is that quantum mechanics applies to computer printouts along with quantum mechanics, but the quantum domain. But ultimately, if you take as a ground rule, as I do, that a solution to the measurement problem must not make a decision about consciousness being outside the domain of physics. It could be, of course, that consciousness is outside the domain of physics, but it shouldn't, a solution to the measurement problem should not depend on taking a stand on that. And so it ought to apply even if consciousness is part of the physical world and subject to the laws of quantum mechanics. And so then universality in its full force would come into play. The second is the eigenvalue-eigenstate link. No value of a quantum observable if the system is not in an eigenstate of it. And the third is our subjective awareness of definite outcomes of pointer systems. Now, so by one, let psi be a superposition of triple product states representing a joint system consisting of a quantum object, say an electron, a pointer system for an observable, say the spin, in a certain orientation, and plus a person, say Jeff Boob, observing the pointer. Now, under suitable assumptions at the conclusion of, say, a spin measurement, Jeff Boob is not in a state of experiencing any definite outcome because he's entangled with the whole rest of the system. And so he has no pure state. He's in a mixed state, but it's not a proper mixture. It can't be subject to an ignorance interpretation on pain of contradiction. And so by assumption two, the eigenvalue-eigenstate link, that he's not in a state, and this directly contradicts what we may, he doesn't have a value he doesn't have a value of this observable, so he's not experiencing a definiteness or the appearance of definiteness. But that contradicts, we may suppose, an instance of three, which is that Jeff Boob tells us he does see that the outcome was up in this particular experiment. Okay. Now, the Everettian response that our subjective sense of definiteness may be itself illusory, an analogy with illusions we have about time, say, corrected by relativistic physics, Pache, Stephen Savitt's lovely talk from yesterday, is, we claim, ineffectual against what I like to call Descartes' demon. even if it only appears to us that we are experiencing definiteness of pointer systems. That appearance itself suffices to generate a contradiction. And one has to just fiddle with what the total state function is and what the observables are, right? And people have done this. So you can get a superposition of corresponding to the situation where Jeff Boob thinks he's experiencing definiteness, and then another component doesn't think that he's experiencing definiteness. And so at some stage in this, it appears to appear, or it seems that it seems, you have to draw the line if we're to make any sense of our experience that confirms quantum mechanics itself. That's Descartes' demon at work. And wherever you draw the line by the universality assumption, you can cook up a state, right, which will not give you definiteness in that respect. And so you'll have your contradiction. So finally, and this is the last slide, I remind you, Bohrian solutions essentially give up universality and don't apply quantum mechanics to the whole universe. Modal interpretations give up the eigenvalue-eigenstate link. As Shimoni has reminded us, taking account of work of Leggett and others, one, the question of universality is an outstanding empirical physical question. We are simply not now in a position to solve the problem, but that doesn't mean it's not a problem. Finally, I want to consider a question raised by Sheldon Glashow. This was in conversation at Indiana University back in the early 1980s. After a beautiful talk that he gave, Douglas Hofstadter and I were having a conversation with Glashow in which we asked him, well, what do you think about these problems, the problem of quantum measurement and these different interpretations and many worlds and all this, And he denied that he understood what the measurement problem was. And so we went through, sort of rehearsed just what I've gone through. And then finally he said, okay, I guess I do understand what the measurement problem is after all. And I see that it is a genuine problem. But I don't have to work on it, do I? And this is so my answer is, well, at least not in Canada, which is still a free country. Thank you. Yeah. Yes, I think that's right, and I have adhered to that in the past. And so, I guess I should say then interpretations or certain modifications. I mean, it would be vague, and how much modification you're going to allow. But I did want to invite discussion of the GRW in the context of these concepts of probability. So that was my just strategy for the discussion. I really have no insufficient understanding of that to make a responsible comment, I'm afraid, but maybe others would. Excuse me? No, I'm just assuming, well, I guess within the framework of this talk, I can just refer to the introduction that I gave with the formal overview, which just stipulates that, generalized probability measures take values in the interval 0, 1. So it's outside the domain of the framework that I'm considering, but I don't know what it would mean to. Yes. Mm.
Does the model interpretation essentially do contextual invariant theories that it assign values to maximal Boolean algebra projection?
It does do that. It does do that, but I think that it goes beyond those as well. I think it goes beyond those as well. I think it's less contextual. Uh, uh, you, you get to assign values to observables pertaining to individual systems, which are part of a whole system, even though they're still entangled. So you get to say that when you observe, suppose you observe a pointer, so you observe the cat, and you get to say that the cat is alive and that Abner-Shimoni observes that the cat is alive, even though you and the cat are still entangled at the end of a suitable interaction with a quantum object. And I don't believe that you're allowed to do that on the contextual hidden variables theories you're talking about, where the observables would be relativized themselves, wouldn't they? Here we have the good old observables that you like, that we know and love. Oh. Yes, right, right. Okay, so I see what you're saying. Yes, yes, okay. All right. So I think your question is whether you ever assign simultaneous values to incompatible observables. And I think that, yeah, I think you do. There are consistency proofs. Well, I'm not sure what you mean by primitive. Uh, I don't. Uh, I don't mean to be able to define it in mathematical terms. I'm talking about physical randomness as opposed to the various precise definitions of mathematical randomness. So there's the Kolmogorov-Chaitin definition of randomness. There's one that goes back to von Mies. There's a Martin Löf. I once looked at a bunch of them. It's very interesting. Many mathematical definitions of randomness, which don't all agree on just which sequences are random, sequences of zeros and ones, let's say. I would expect there to be a connection. So no, I'm thinking of physical randomness in the sense of a breakdown of classical causality. The idea that certain events simply aren't, there is no sufficient reason, sufficient cause of those particular individual outcomes. There is only law-like behavior in a statistical or stochastic sense. So that's the notion. It's a physical randomness notion, and I believe there would be connections. One would expect there to be connections between that and a good mathematical definition. That is, if you do a sequence, say, of Stern-Gerlach measurements, or look at an ensemble and order them in a certain, in a reasonable way, you should generate sequences of zeros and ones that are mathematically random if your mathematical definition applies to long enough finite sequence. That's another problem. Some of the mathematical definitions only apply to infinite sequences, and then what do you do, right? So that's, I mean, I think that quantum mechanics is one of the deepest features of it, or of the quantum world that we seem to occupy, is this phenomenon of physical randomness. And of course, we get some understanding of it from the physics itself.
Does Bob Gribble's consistent history view fit into this scheme at all?
Another good question for further thought. I don't understand it well enough to say how. I don't understand. I mean,
Talk about probabilities of this set of things or this set of things.
it's set in the. It sounds to me as though, as I understand it, the overall framework is a one-world Everett. It's a one-world version of the Everett interpretation, spelled out in some more detail. And I don't understand how the one-world version of the Everett interpretation manages to make any sense of probability. Because probability of what? Nothing happens. And if nothing happens, what are probabilities?
I should probably explain why I said humbug, and then said humbug twice.
Oh, I didn't even hear you.
Well, I said humbug the second time to emphasize the first one. It was related to your remark where you said that the people who are sitting in subjective 1, subjective 2 seem to give up the goal of physical inquiry. I don't know if that was exactly your phrase. And I think that that's an unfair characteristic. I don't believe that I've ever met anyone who sits in that quadrant of your chart, the ones that I call quantum Bayesians. I don't believe that I've ever met a quantum Bayesian who didn't believe that what physics is about is trying to make some description of the real world, the world that's out there, independently of that agent with his subjective degrees of belief, whose subjective degrees of belief are about these bad words called measurement. He still thinks that physics has something to say about that, but it's at a higher level of description than simply saying that probability of property changes or that measurement outcomes somehow property of the system.
Well, yeah. Okay, well, I take the point that there may be many good intentions on the part of subjective proponents, and I even hold out. I mean, I can even allow that maybe they will succeed in some way in fulfilling this goal. But it seems that there's a terrible problem here, because if your notion of state as I'm taking a state to furnish probabilities. That's what states do. And if the probabilities they furnish are understood as degrees of belief, then how can the states explain the frequencies that we actually observe? Degrees of belief need to reflect the frequencies. There needs to be a correspondence, or we're not rational. But this puts the cart before the horse. The frequencies, we adjust our degrees of belief to fit the frequencies. That's David Lewis's principal of Bayesian probability. If you have good information about frequencies, then you better reflect that information in your degrees of belief. But then you can't explain the frequencies by reference to the states. Now, maybe there's some other apparatus that you can bring in that will explain the frequencies, and that remains to be seen. So that's why.
So let's thank the speaker again.
Thank you.